Hello guys, today we're going to see frequency response methods. Welcome. We have seen on continuous time domain systems some standard procedure in order to analyze frequency response of a certain system. But happens that in digital domain, in computerized control, those methods can be applied, but using what we know as bilinear transformation. So the general design procedure is going to be in the W plane. W meaning our toasting variable. So first of all, we have to obtain the transfer function in Z domain and transform this transfer function in order to obtain G of W. Next step is going to be to substitute this W equals to J nu. Why J nu? Because remember that this W is again a complex variable, so it has a real part and imaginary part. So this nu is kind of a fictitious frequency, okay? And we're going to analyze and we're going to design in this fictitious frequency domain nu. It's a nice thing to do to obtain the body diagram of J nu, just in order to know about the behavior of the system. And also it's useful to read static error constants like position, velocity, and acceleration from the body diagrams, and also of course the robustness margins from the diagram, meaning the gain margin and the phase margin. Then we would like to proceed with the standard procedures of continuous control design in frequency domain in order to find a proper transfer function for the controller. Finally, we need to come back to the domain in order to instrument the controller. So let us remember a little bit about robustness margins. We know gain crossing frequency, nu G, is the frequency for which the magnitude of the open loop transfer function is unitary. Okay, it means that the magnitude of the output equals the magnitude of the input. With this frequency, we find the phase margin, and this phase margin is the required additional delay in the gain crossing frequency to make the system unstable. And we may use this formula here: gamma equals to 180 degrees plus the angle of transfer function evaluated in this gain crossing frequency. For the gain margin, we first find the phase crossing frequency, which is the frequency at which the phase angle is minus 180 degrees. And gain margin is obtained as here kg equals to minus 20 times log of the magnitude of the transfer function evaluated at this phase crossing frequency. This is always in decibels. Here we may have a plot here, for example. Sorry for the Spanish. I have the gain crossing frequency here, and here comes the phase margin, and we have the phase crossing frequency, and we have the gain margin here. Okay, so let's see an example. Assume, for example, we have a g of s equals to 1 over s times s plus 1, and we have a typical zero order hold. Let us consider a sampling period equals to 0.1 seconds. And the idea here is to find the phase margin and determine the static error coefficient for velocity from the magnitude body diagram. So, first of all, we have to normalize the function as usual. And we have here, well, first of all, of course, we need to obtain this G of W. G of W can be obtained using program CC also, which is just apply the W transform to this transfer function, and then normalize the function just in order to have all polynomials as independent term equals to 1. Okay. We use program CC. The instruction is body, just body here. And take a look. The only thing that we have to do is to right click in the mouse, and we're gonna find that, for example, we have at this frequency 0.78 radians over second, we have a phase margin of 49.8 0.58 degrees as phase margin, and at this other frequency 4.51 we have the gain margin of 26.17 decibels. We're not going to see this delay margin, okay? Problem, remember? So we need KB to be 4. Then we use this restriction. This velocity error coefficient should be equal to 4. So we can find this static error coefficient using the limit, for this case for J nu tending to 0, times J nu times the controller here times the transfer function of the plant, okay, which is a standard procedure. So finally we have here K equals to 4. Then, in order to compensate this slope, what we're going to do is to locate a 0 exactly at the first pole of the plant. This is, we're going to make alpha equals to 1. Doing this, what we're going to have is that KB is going to be exactly the frequency, the gain frequency. For doing this, let us obtain gamma. Gamma is going to be 45 degrees equals to 180 degrees, which is the formula, plus the angle of the whole open loop transfer function here, including alpha and beta. But if you can see this term here, alpha, is going to cancel with this other term of the plant here, okay? So the only variable, the only unknown that we're going to have is this beta. So let us use Wolfram alpha to solve this. So we're going to have this equation here, which is straightforward to solve using this Wolfram alpha, and we're going to find that beta equals to 9.33 and so on. So what we have here is this alpha here compensates initial slope, and we're going to have another pole at this point here. So the red one is a controlled system. We can see this is the real system, and well, the controller is in terms of nu, I'm sorry, this should be nu instead of omega, and in terms of Laplace variable we have this. So actually what we have is this J nu controller. In terms of toasting variable, we just substitute J nu with W. In Z domain, we just come back to C domain using inverse toasting transform, and we have this expression here.